Hey, algebra students. I know we've been hitting you pretty hard with the last couple of lessons, and so I'm hoping that this lesson is just a little bit of a, oh, how should we put it? I'll just say it's easier. Learning target 7, solve systems of non-linear equations. Well, you know what linear equations are. They make straight lines when you graph them, and we've done systems of linear equations this unit so far, and so this lesson today we are going to be solving systems of non-linear equations, and we've also worked with non-linear functions throughout this year. So what is a non-linear system? Well, it's simply a system of equations, just like we've been working with considerably here. So a system of equations with one or more non-linear. So we've got lots of examples of nonlinear functions. We've got exponential, we've got quadratic, we've got cubic, we've got quartic, we've got circles even that we've talked about so far this year. So a system of equations with one or more nonlinear equation. All right, and well, you know what a solution to a system of equations is. It's the solution, or it's the coordinate that makes, or the xy value that makes both, or all three, equations true statements. And so it's the same thing here. Um, it's the x and y, or x, y, and z if we had 3, the x and y values that make both or all equations true. Okay, and so in that sense, it's no different than what we had before, except that because we have nonlinear functions, it means we might have more than one solution. In fact, so you know that when we graph these, it's the place where they both cross. So it's the intersection points. Well, you know, if I have a linear and then a nonlinear, like a quadratic, you can see that there's a good chance that you would wind up with two coordinates, two sets of values for x and y that would make both of these equations true. And so very often we will have more than one solution. Of course, you know, it's possible to have one solution, like right here. There's just one solution. There's one place where they intersect. In fact, there could be 0. You can see that, you know, there's nowhere where this line intersects that parabola. But, you know, there are more than one solution as possibilities. Okay, so a few quick examples. Solve the system and then verify with a graph. So what we've got here is, this is a quadratic. You can see the greatest exponent is 2. If I wanted to graph this, I could, you know, solve this for y, and I'd have maybe negative y equals negative x squared plus 4. And so this would be kind of the same thing as y equals positive x squared minus 4. So that would be a parabola with a vertex here at negative 4. You graph a few points, and you could see very clearly that we've got a parabola that looks a little bit like that. And if I were to graph this one, it's in standard form, so I'd graph using the intercepts. When x equals 0, y would equal negative 2. And when y equals 0, x would equal negative 2, so that's right there. It looks like that's a pretty easy spot to find. If I connect my lines here, you can see that my two graphs intersect right here and right here. So right off the bat, I've got a pretty good idea that my solutions are negative 2, 0, and 1, negative 3. So let's keep that in mind as we go about solving this algebraically. I'm looking at it, and I can see that if I used elimination or combination, the y's would cancel out. So let's see what happens when we do that. Well, these are not like terms, so I can't really combine them, but I'm going to try. We'll just say x squared plus x. The y's, of course, cancel out. And then I've got 4 minus 2, which is 2. Well, it looks like this is also a quadratic. And so we'll go ahead and set it equal to 0 and see if we can factor. So x squared plus x minus 2 equals 0. Well, this does look factorable. And I have x, I can have 1 plus 1 minus factors of 2 that would give me positive 1. Well, 2 and minus 1. And now I use the zero product property. I get x equals negative 2 and positive 1. And look at that, negative 2. Positive 1. Now we need to find those y values, and so I'm going to plug these numbers in separately into either of the equations. I'm going to pick the bottom one, so maybe I'll change colors here since we're headed to a different idea. And we'll say, all right, when x equals negative 2 plus y equals negative 2. Well, add 2 to both sides, and I get y equals 0. When x equals 1, the other value here, I'd plug 1 in, plus y equals negative 2. Subtract the 1 from both sides, and I get y equals negative 3. And so, ultimately, my final answer here is when x equals negative 2, y equals 0. Hey, look, that's that one. And then when when x equals 1, y equals negative 3, ta-da, we got the matching one right there. And so, there it is. That's a system of nonlinear equations. All right, let's try another example. Now, I'm looking at this one, and I'm already thinking to myself, gosh, all right, I know that this one is a circle, and it has a radius of 2, so I wind up with maybe something that looks a lot like this. This one, not as common as a hyperbolic function. If you were to graph this, maybe using Desmos or something like that, you would see that it looks a little bit like this. I'm trying to hit these points right there. Okay, so if you were to graph using a graphing tool, you would see that that's the system there graphed out. And so we got negative 2, 0, and 2, 0. So let's keep that in mind as we solve this algebraically. Now, when I put this together, notice, again, the y squareds will cancel out the y squareds, and luckily for us this time, the x squareds are going to match up. So I wind up with 3x squared. The y's cancel out, or y squareds cancel out, and I get 12. Divide both sides by 3, and I get x squared equals 4. And so x is going to equal not just 2, but positive and negative 2. And wait, look, there it is. Let's go ahead and plug those back in and solve for y. I'm going to pick the top one. So when x equals 2, I get 2 squared plus y squared equals 4. Well, 2 squared is 4, so I subtract 4 from both sides and I get y squared equals 0. And, well, the square root of 0 is 0, and so y equals 0 when x equals 2. When x equals negative 2, well, you'll notice pretty much the same thing happens. Negative 2 squared is positive 4. And so subtract that from both sides and I get 0. And of course, y still equals 0. So my final answers are when x equals 2, you get y equals 0. And then when x equals negative 2, you still get 0. And that matches up with what we see graphically and algebraically. And so we feel really good about our answer. All right, the last one that I've got for you here actually takes a look at absolute value. And so if you remember absolute value functions, if we solved for y here, we'd get negative absolute value of x plus 4. Well, this shift would shift the vertex of that v up 4. The negative would flip it upside down, and since there's no shift here or scale, we're going to just go at 1, so down 1 over 1. So it looks something like that, and then look a little something like that. That's not very great, but it'll do. Okay, and then this one up here is another circle with a radius of 4. So put some points there, connect those, and I've got my circle. Okay, so those are my two functions, and it looks, if I were able to draw a little better, that my solutions are right here, and right here. So I'd have three solutions at 0, 4, negative 4, 0, and 4, 0. Okay, so let's see what this looks like algebraically. Here's what I'm going to do. I'm actually going to use substitution. When you've got this absolute value, I could just solve for the absolute value. So I could say the absolute value is equal to 4 minus y. And I can substitute that in. Now, remember, you'd have to do positive negative version here, but because I'm squaring it, that all kind of goes away. I'm squaring positive and negative version. It's about the same thing. So I'm just going to say 4 minus y squared plus y squared equals 16. As I expand this out, I would get 16 minus 8y plus y squared equals 16. Combine a couple of like terms. I'm going to turn it around, make it look good. So we'd have 2y squared minus 8y plus 16 equals 16. Well, I could divide everything out here by 2 and I get y squared minus 4y plus 8 equals 8. Clearly, those 8's will cancel each other out, and so I've got y squared minus 4y equals 0. All right, well, it's not a trinomial quadratic, but it is still a quadratic, and so I can solve by factoring, if I can factor, which I can. I can factor out a y, in which case I'd be left with y minus 4. And the zero product property leaves me with y either equals 0 or positive 4. Hey, look at that. My y values are either 4 or 0. All right, so now I'm going to go back in and I'm going to plug these in for y and then solve for x. Again, you can pick either. I think I'm going to pick the top. So I've got x squared plus y squared, which is 0 squared, equals 16. That means you got x squared equals 16. Square root of 16. X is equal to positive and negative 4. So when y equals 0, you get 4 and negative 4. Great. Let's see what happens when y equals 4. You get x squared plus, well, y is now 4 squared equals 16. Well, x squared 16 minus 16 is 0. Square root of 0 is 0. And so when y equals 0, x equals 4. And so, or negative 4. And when when y equals 4, then x equals 0. And these are the 3 points here that match up there. And so this is what I'm expecting you to be able to do with non-linear systems of equations.